First of all, thank you for coming to my talk. I'd like to thank the CAIAC for awarding my thesis. I'd like to thank my supervisors at the University of Toronto, Alan Borden and Nisarg Shaw, for their great supervision. And I'd like to also thank my current postdoc host, Omar Lev at Ben Gurion University. So, as you can probably infer from my thesis title, there's three distinct directions my research takes, but all are based on the concept of voting. So here's an example of a vote or a very recent election, and it's the last United Kingdom or UK election. And here, the UK has been partitioned into regions, also known as ridings or electoral districts, and each of these ridings is going to have a vote to pick a representative, or they're going to pick a political party to represent that riding, a member of parliament, also known as an MP. And the job of this MP is to represent the needs and requirements of their constituents to the government. We have the same system here in Canada, and there's a very similar system in the US called the congressional system. So you can see that the UK has been color coded, each region by which party won that region. And if you sum up across all the votes in the nation, you see the Conservative Party on the bottom right chart got the most, about 14 million, and that also happened to be the most MPs, or seats filled, around 350. Now, in this case, they had the most MPs, which really translates into the most political power, and they actually went on to form government. But you don't have to have a perfect correlation between vote and political power or seats. In this case, the Lib Dem Party, they got the third most vote, but they won the fewest MPs. And that's because their vote is very inefficient. So, like I said, my research looks at three different directions. I consider it the three roles of types of agents involved in elections. The first is the role of the voter, and in particular, the strategic voter. So here I'm interested in how voters can lie about their honest preferences in an attempt to get a better outcome for themselves in the election, and how this manipulation impacts society. The second is the role of the mapmaker, or gerrymandering in the United States. And here we examine the people who actually designed those electoral ridings, like you saw in the UK. And if you think about it, you could have designed very different ridings to get a different outcome. So you could design a very partisan outcome for your preferred political party if you were somewhat nefarious. And finally, the role of the political party. Here, I'm interested in the party primary process. This is the process that parties use to whittle down the set of candidates who go on to represent them in the general election. So, if you think back to the last United States presidential election, the Democratic Party had a primary process where Joe Biden and Bernie Sanders were vying to be the Democratic representative. This internal election eventually picked Joe Biden, who went on to represent the Democrats. Here, we're interested in how does the primary process impact the utility to society. Now, because we're very time limited, I won't be able to talk about the first or third topic. I can answer questions about them in the Q&A, but instead we're going to entirely focus on the second. But before we get into map making or gerrymandering, we should answer this question: why is this artificial intelligence? And it is something I've actually been asked by reviewers and colleagues. And I see my work and work like it as AI for two reasons. The first is we can use AI techniques to assist in human voting. This isn't so relevant to my research, but definitely relevant to my supervisor Nisarg Shaw's research, in particular a project he's involved in called RoboVote. And by using our knowledge of AI, we can help groups of people come to high quality decisions. So even if they have conflicting preferences, we can find a communal decision that maximizes utility or minimizes the unfairness to them. The second reason, and this is really the justification for my research, is AI techniques can help us study and design elections. So by this, I mean things like we can use game theoretic models to capture the behavior of strategic agents, such as the strategic voter in our election models. But what we'll focus on today is designing electoral districts like those you saw in the UK using automated techniques. And these districts that are designed by automated techniques are often able to match or even surpass human design districts for various metrics. Now, by being able to automatically design districts, we're able to better study and understand fundamental issues facing district elections. So now let's formally define gerrymandering, and we're also going to talk about the urban-rural divide. And for now, it's just sufficient to know that it's a particular pattern for how voters distribute themselves. So let's actually introduce districting. And from now on, we're going to work in the graph model. This is actually how the real data is presented. And in this example, which is simplified, we're going to divide this graph into 5 districts. Now, here's what I mean by that. Each node in the graph represents a precinct or neighborhood. And this is the smallest level of data where votes are aggregated at. And edges between nodes represent physical adjacencies. So this means neighborhoods that have a physical boundary with each other. What we want to do is divide these nodes into 5 districts. Each node is going to have one voter in it, or one person living in it, and they're going to be a red or blue voter. This is greatly simplified. Actual nodes have a few hundred to maybe 1,000 voters of different mixes living in it. What we want to make sure is each district has an equal population, so in this case, they're going to have the same number of nodes per district, although you're usually allowed a little more flex than that. And each district must form a connected subgraph, so I should be able to walk from point A to point B in my district for any 2 points without having to cross into a second district. There are many ways to do this division. Here's one perfectly legal one, and someone called this the fair plan. You notice the vote share matches representation. Red with 60% of the vote gets 60% of the seats. Districts form convex shapes, and they're actually homogeneous. That is, everyone inside a district, at least according to the data we have, the voting intention is identical. And this last point could either be a good or bad thing. You could argue either way. This second plan is the red favoring one, where we've drawn these horizontal strips, and their 60% of the vote wins in 100% of the districts. So I would say this is less fair than the original plan we saw. I think most people would agree it is less fair also. And the districts are convex here, so it does have that going for it. Here's the final plan we're going to look at, the blue favoring one, where these more contorted non-convex shapes have stretched blue's 40% of the vote to winning 60% of the districts. And really this, and I would actually say the last, are examples of gerrymandering, where you draw districts that are unnatural, although you could argue the previous one, which was convex, was somewhat natural, in an attempt for partisan gain. So let's actually look at what happens when partisans do draw the districts, because in many states, it's the politicians who are in charge of the government at the time who control redistricting. In some states, it's an independent commission that handles it. In Canada, it's also in an independent body. So in these cases, you don't actually have to worry about partisan gerrymandering. Now, here's an example of alleged partisan gerrymandering. In 2011, during the last redistricting cycle, the Republicans controlled Pennsylvania's government, and they proposed this plan that was eventually implemented. It was argued all the way up to the Pennsylvania Supreme Court that this was an unfairly gerrymandered plan, and the court actually threw this plan out and had a new one implemented in 2018. Now, the arguments against this plan were the districts were very unnatural, highly non-compact, and very oddly shaped, and the outcomes were very partisan. They were outlier outcomes. Now, we've color-coded this plan with data from the 2016 presidential election, which was close to a 50-50 vote share. Red districts are won by Republicans, blue by the Democrats. And in this particular case, the Republicans win about 2/3 of the districts. There is a really interesting pattern, though, to where the Democrats win. If you notice, it's entirely in the city of Pittsburgh and Philadelphia. And this is an example of the effects of an urban-rural divide. The Democratic vote is very strong in these cities, so they're able to win districts in these cities. In fact, that's the only place where they're able to win. This isn't just a Pennsylvania thing, it's not just a United States thing, it's a thing in most Western democracies, including Canada. And it's so pronounced and widespread that political scientists have started saying the labels of left and right party don't really mean what they used to mean in the traditional sense. The left party really is the party of urban issues, and the right party really is the party of rural issues. So let's look at that node level or precinct level data I was talking about. Here we've color-coded, according to the 2016 presidential election, blue nodes are Democratic voting nodes, red nodes are Republican voting nodes, and the shade of pink in between kind of is dependent on the gradient of the vote. You have these Democratic centers like I talked about, Pittsburgh and Philadelphia. But you also have these other smaller urban regions like Erie, Scranton, and Allentown that go Democrat. And it's this rural region between the cities where the Republicans have their voters. And like I said, this is not just a Pennsylvania thing, it's not just a United States thing. This asymmetry, this urban rural divide, is something that's very common in most Western democracies. Now, it's been argued that this particular urban rural divide, or the urban rural divide in general, is very susceptible to gerrymandering, and that the alleged Republican gerrymandering from 2011 was so effective because of this asymmetry in the vote. So, this asymmetry in voting intention, this urban rural divide, it really motivates the rest of my research. I want to know, how does it impact redistricting? How does it impact the ability of parties to gerrymander? And how does it impact districting that was drawn with neutral goals in mind? And to answer that, we'll look at two distinct but related projects. So the first project was looking at how the urban rural divide directly impacts the ability of either party to gerrymander. Now, to do that, we worked with simulated data to remove any confounding effects so we could study the urban rural divide directly. And for what we did was we created a model for strengthening the urban rural divide. And we worked in grid graphs, which are kind of the simplest planar graph you can have. We would locate one city center in our graph, and depending on the strength of the urban rural divide in our model, we would concentrate the urban vote share around that city center. So at one extreme, when there's no urban rural divide, there is no concentration of urban vote around the city center. Here we have blue nodes going for the urban party, red nodes going for the rural party, and a shade of white for nodes which are split between the two parties. And as you see, there is no pattern. It's just completely uniformly random. The urban center isn't actually a center of urban party support. But we can increase the urban rural divide in our model. So now you have this urban center forming with strong urban support, but it's still pockets of urban support in the rural regions. An even stronger divide basically pulls most of the urban support into the urban center, although again, still a few pockets of urban support and bipartisan support in the rural regions. And at the most extreme, you have a complete bipartition where the only spots of bipartisan support are where urban meets rural, or the suburban regions. Now, to actually do the gerrymandering, we used an integer linear program as a subroutine for a hill climbing approach. Unfortunately, the optimal integer linear program struggles to find solutions even in these small simulated examples, and this is a very common theme in redistricting literature. Finding optimal solutions is very hard. But our program performs quite well. In this example, where there is no strong urban-rural divide, you see it's able to gerrymander quite effectively for either party. So here, the rural party has 55% of the vote share, and on the left, when the urban party gerrymanders with their algorithm, they're able to win 54% of the seats. So their very weak 45% of the vote is now a majority of the power. The color of the district itself is the party that won it, so red won by the rural, blue won by the urban, and the shade of the color itself is how strong that win was. And there really is no pattern here. The urban party just wins seats all over the place. If you look at the rural gerrymander on the right side, you see their majority of the vote, 55%, is now 96% of the seats. They've won everything. And again, there really is no pattern to it. There's just this one little district that they couldn't take from the urban party. Now, if we look at an example of a very strong urban-rural divide, and do the gerrymandering again, so 55-45 rural party vote share, again, you see on the left, the urban party still is able to win about 56% of the seats, so they're able to stretch into a majority, but there's a very striking pattern here. They have very strong wins in the urban center and weaker wins in the suburban, where urban meets rural, and they can't win anything in their rural regions. And it's very similar for the rural party on the right here. But now, instead of winning basically every seat, they can only win about 66% of the seats, and they only win strongly in their rural regions and marginally in the suburban regions, and they can't crack that urban center. So these are very similar gerrymanders. They only actually differ in the suburban. Those just weren't two cherry-picked examples. Across many different strengths of urban-rural divide and many different generated maps, we saw the following pattern emerge. So here, the y-axis is the term we coined the gerrymandering power, and this measures how far you're able to stretch your vote share beyond what is proportionally fair. So a gerrymandering power of 0 would mean when you gerrymander, you aren't able to get any more seats than what is proportionally fair. 60% of the vote turns into 60% of the seats. But if you have a positive gerrymandering power, that means you can turn that 60% of the vote into more than 60% of the seats. And you can even have a negative gerrymandering power, which means if you could have any districting you want, it wouldn't even match what is proportionally fair for you. So in this graph, the x-axis then represents the strength of the urban-rural divide. 0 means no urban-rural divide, so that's like the first example we saw that we gerrymandered, and 10 represents a very high urban-rural divide, so like the last example we gerrymandered. Red lines are when the rural party gerrymanders, that's their gerrymandering power. Blue lines are when the urban party gerrymanders, their gerrymandering power, and the shade of the line represents their vote share. So these dark burnt looking lines are when the rural party gerrymanders and has a very high vote share, and these kind of light greenish lines are when the urban party gerrymanders and has a very weak vote share. Now, there is a very consistent pattern going on here. Concentration limits your ability to gerrymander. Early on, when you have a not weak vote share, you're able to achieve seats almost anywhere, like that first example, and you're able to stretch your vote quite far. So you have a very high gerrymandering power. But when the urban-rural divide becomes very strong and the voters split apart, your ability to gerrymander is incredibly limited. It's really only where urban meets rural, these suburban sections where there is some bipartisan support, where you can make any gains. So, it seems like the urban-rural divide, at least in its extreme, can be a guard against the extreme effects of gerrymandering. And finally, I'll note that the rural gerrymandering power is always on top of the urban gerrymandering power, so it seems like the rural party has the advantage when it comes to gerrymandering. And this is something that we'll also see crop up in the next section when we deal with real data. The second project we undertook was gerrymandering with real data and looking at compact districting. Now, perhaps unsurprisingly, real data is much harder to work with than the simulated data from before, and our previous method is no longer sufficient. Instead, we built a simulated annealing approach, which is based upon the metric geometry and gerrymandering group, or MGG's, gerry chain, which itself is a randomized algorithm for iterating districtings. Our program is highly modular. It can create highly compact districts, it can create highly partisan districts, and it can even blend them, creating partisan districts which are compact. But what we're most proud of, and we think we are the first to do this, is we have a tool, or a fully automated tool, that is able to match handcrafted districts created by election experts. And for this, we used the gerrymandering project from Nate Silver, pictured here, of 538, where he and his team, they created various districtings to study redistricting and gerrymandering in general. Now, their plans were mostly handcrafted, and they were done for various goals such as compactness and partisanship. And when it came to partisanship, our algorithm is able to nearly match his outputs in terms of how partisan they are. So what Nate Silver and his team did for partisanship was something called high probability wins. So before we were just doing 50% plus one of the vote to win a district. Instead, they took previous election data and turned that into the probability a target party would win a district. Here in North Carolina, which has been gerrymandered by them to favor the Democrats, red districts are more Republican-leaning, blue districts are more Democrat-leaning, and the intensity of the color shows how probable that district is to go for the party. And their goal was to draw districtings where their target party won as many districts as possible with high probability. That's about 82%. They didn't actually release the method to calculate this probability or even the mathematics behind it, but we think we've been able to reconstruct it based on what data they have released. So 538 did this for all the states which have multiple congressmen. They were able to do that because they paid for privately held data which shows previous election results. Unfortunately, that's not available to the public for free. We were able to get near equal data for 5 states, Pennsylvania, North Carolina, Wisconsin, Massachusetts, and Maryland. So we now have 10 different districtings, so in each of those states, one for the Republicans and one for the Democrats to compare against. And in 9 of those 10 plans, we were actually able to match or even exceed 538, winning as many or more high probability districts for our target party. Now, I'm not willing to say just yet that our method found a better solution, because they did have absentee ballots at 538 and we didn't have complete absentee information. That's mail-in ballots. So it's not a perfect apples to apples comparison, but it's pretty good. And in fact, in the one state we missed, or the one case we missed, was North Carolina for the Democrats, where they got one more high probability win than we did. So the first question we want to answer with our tool is, are compact plans fair? That is, are plans designed with only compactness in mind fair to both parties? And the reason we want to answer this is because many states, and in Canada, we say we should design districts which are highly geographically compact, although we don't often define what compact means in mathematical terms. So, because there's not a universally agreed upon definition of compactness, we use two popular ones, the convex hull and Pulsby-Popper score. I can talk about them more in the Q&A session, but they are very popular ones in the literature around redistricting. Now, the bottom here is our algorithm redistricting Pennsylvania for the convex hull score. The top is the 2011 plan, remember the one that I said was thrown out by the Pennsylvania Supreme Court. And again, we've color-coded both of them using the 2016 presidential election data. So, right off the bat, this passes the eye test. Our algorithm's convex hull plan looks far more compact than the 2011 plan, and you could argue for really any definition of compactness. In fact, our convex hull plan and Pulsby-Popper plan had the best score for their respective metric in every state we worked with when compared against any other plan we had access to. So our algorithm is very good at generating highly compact districts. That being said, are these districts any more fair than the existing ones? Just looking at this win-loss data, you see our algorithm's convex hull plan has about the same number of wins for each party as the 2011 plan. And remember, that was the plan that was allegedly gerrymandered and thrown out by the Pennsylvania Supreme Court. Well, to actually answer that, we don't just use the binary win-loss criteria. Instead, we use the generalization of the partisan bias score, which is built on the uniform swing model. I can talk about them more in the Q&A, but effectively, we just construct a series of hypothetical elections that are close to the actual election outcome, and we measure how far these hypothetical elections are from what is proportionally fair. Now, how far those hypothetical elections are from fair is plotted in this bar graph here. It's been divided into 3 states, Wisconsin, North Carolina, and Pennsylvania, and the value represents how much these hypothetical elections favor the Republican Party over proportional fairness. Each bar represents a different districting. So, for example, the blue and green bars are our convex hull and Pulsby-Popper plan. The yellow bar is 538's compact plan, which is a compactness definition that blends geography and population distribution. The purple bar is the 2011 plan, created in the last redistricting cycle, and the gray bar is the updated plan, because in North Carolina and Pennsylvania, their original plans were found to be illegal, so they had to be redrawn. Now, the most striking thing here is, not one of these bars is reporting a negative value. Every single plan, regardless of the intention when drawing it, favors the Republicans. So this is just a huge advantage they have. That being said, compactness can help. If you look at North Carolina, the 3 compact plans are far less Republican favoring than even the updated plan is. You have a similar pattern in Wisconsin, the first state here, where the compact plans are slightly less Republican favoring than the existing plan. But if your main goal is to achieve a proportional or fair outcome, then maybe ignoring compactness could be more beneficial. In Pennsylvania, the updated plan is actually less Republican favoring than any of the other plans, including our neutral compact ones. I should point out, this plan is not as compact according to any of the compactness metrics as our plans. That information isn't shown on this chart, but there was a significant gap in the compactness score. So it's our speculation, and it's also been commented on by some election experts, that this updated plan may have been designed with some notion of fairness in mind, and compactness was really a secondary goal. Unfortunately, we haven't been able to find any comments from the plan designers themselves. So the second problem we wanted to use our tool to solve was doing partisan and compact gerrymandering simultaneously, or gerrymandering and getting away with it. Now, the idea here is compactness often is touted as a tool that can be used to prevent gerrymandering or detect it. That is, you could set a compactness threshold according to some metric and say any plan that doesn't meet this threshold should be thrown out, or any plan that doesn't meet the threshold has been gerrymandered. So we want to understand how these hypothetical compactness thresholds impact the ability to gerrymander. As I said, our algorithm is very good at gerrymandering and doing it compactly. Here is Pennsylvania. We told our algorithm preserve 11 wins for the target party, Republicans on the top, Democrats on the bottom, and here wins are just 50% plus 1 vote. And we told it also maximize the Pallsby-Popper score, which I said is a very popular measure of compactness. Now, does this actually limit your ability to gerrymander? And the answer is it's a bit tricky. Here's our summary for Pennsylvania. The y-axis measures the gerrymandering power. So remember, that's how far you're able to stretch your vote into seats beyond what is proportionally fair. Red lines are the Republican gerrymander, blue line is the Democrat gerrymander, and the x-axis is various Pallsby-Popper score thresholds. The horizontal black line here is proportionally fair. When your gerrymandering power line is above this, that means you're able to stretch your vote share beyond what is proportionally fair, and when it's under it, that means you can't even achieve what is proportionally fair if you could have any districting you want. So a Pallsby-Popper requirement of, say, 30 won't restrict either party in any way. The outcome they get here is just as good as the one as when there was no restriction in place. On the other hand, if you have a very high Pallsby-Popper requirement, say about 45, you see it does greatly limit the ability of either party to gerrymander. But it's a bit of an uneven tool now. The Democrats, if they were to gerrymander, they couldn't even get proportionally fair outcomes to themselves. Their gerrymandering power is negative. The Republicans, although greatly limited, still are able to stretch their vote share a bit beyond what is proportionally fair. And finally, if you look at the Pallsby-Popper scores of the 2011 and 2018 plans, the updated one, you see neither of them are sufficient to limit gerrymandering in any way. In both cases, the parties could gerrymander without any loss of ability and match those compactness thresholds. Now, also you should notice that the red line is always above the blue line. That basically means at any level of compactness threshold, the Republicans are able to better stretch their vote share than the Democrats. And this was a consistent pattern across all the states we looked at in North Carolina and Wisconsin. The existing plans were not enough to limit either party in gerrymandering, and it was often the case that the Republican gerrymandering power line was above the Democratic gerrymandering power line. So this should really hammer home the point that this urban-rural divide, this asymmetry in the vote, more negatively impacts the urban party. When they engage in partisan redistricting, the urban party is not as good at it as the rural party. And solutions such as compactness, they seem like a tool that is unfair, more negatively impacting the urban party. Even totally neutral plans, which only optimize for compactness, still favor the rural party. So that's it for my talk. If you have any questions, I'll be able to answer them in the Q&A session. I want to say thank you for listening to my talk. I hope you did enjoy the talk. Ironically, I'm not so sure the namesake of gerrymandering, pictured here, Governor Gerry, would have enjoyed it. Apparently, he actually disapproved of the practice.